So I'm Yun Pang. Now I'm going to present our work made by Michael, Peter, and me. So to the motivation why we like to do this is that the share of electric vehicles has rapidly increased in the vehicle market in the past, I think, 8 years. From 2015 to 2023, the number of electric vehicles has increased from 1 million to more than 40 million. So the related facilities need to be planned, implemented, and enhanced to meet the demands of EVs, electric vehicles. And the energy consumption models then can facilitate the planning work, strategy policy assessment, and together with traffic simulation and emission models. So right now, as I think most of you already know, we have 4 models in SUMO. And actually, it is not clear yet how well these models can reflect the real battery consumption and which model could be suitable to which conditions. And also, we are also not clear yet what possible differences in battery consumption there will be between these models. So we tried to address these questions by comparing these 4 models with 3 case studies. So here you will have the general overview about these 4 models. They are HABEVA, PHEMlight, EVM, and MMP EVEM. And the first 2 models, they estimate energy consumption according to the aggregated data collected across Europe. And besides of the battery electric vehicles, these 2 models also calculate energy consumption of hybrid electric vehicles, fuel vehicles, and their emissions. And in comparison to that, EVM, which was developed by Kurczveil and López, only looks at battery electric vehicles and also the vehicle types in detail. So that means 12 parameters per vehicle type are necessary. And it applies also to the MMP EVM, which was developed by the Aachen University. And here, this model needs 16 parameters per vehicle type. So to the method used in HABEVA actually is polynomial curve fitting with the given data for each vehicle category. So that means when you use HABEVA or PHEMlight 5, you only need to define the vehicle type or vehicle categories, sorry. But for PHEMlight EVM and MMP EVEM, they calculate energy consumed by different traffic movements and also on board systems. That is the constant consumption. And if you want to use PHEMlight, maybe you need a license if you would like to use more than 2 free classes. So you have to buy the PHEMlight. But the other 3 models, you can use it freely. So that's a general idea about all these 4 models. And right now, the default model in SUMO for emissions is HABEVA 3, just like we heard before. And the default electro energy consumption model is the EVM, is the default model. So let's continue. As we just see that detailed vehicle characters can be considered when using EVM and MMP EVEM, but not HABEVA and PHEMlight 5. So it is not actually fair to directly compare these 4 models. So we tried to extend the model parameterization firstly, and then we compare the model. And at the moment, EVM and MMP EVM, they are actually already completely parameterable in SUMO. So there's no need to do this work. And for HABEVA, there's no option to do that. Just I mentioned it's just a curve fitting work. So we put our focus on PHEMlight 5, and we selected 9 parameters. They were actually separately defined in the original PHEMlight 5 file. So we select them, and then we make them parameterizable so that everyone can just define these parameters in SUMO vehicle type. So same like the parameters in EVM and MMP EVM. So after the model parameterization, we did the model comparison. So firstly, we used the test cycle of the World Harmonized Light Vehicle Test Procedure, that is WLTP, which has replaced the new European driving cycle since 2017. And this procedure aims to better match the laboratory estimates of energy consumption and emissions with the measurements of on-road driving condition. And we used 5 different vehicle types according to the paper MMP EVM by Koch et al. The main reason is that we can then directly compare our result with their result. And they already collect many data about the vehicle characteristics and also the real data from the manufacturers. And then we use the WLTC dataset class 3B according to the power, the weight, the maximum speed of the vehicles. And we set all constant power consumption to 360 watt. And at the end, we used the SUMO tool emission driving cycles to run the WLTC with 4 different phases. As you can see here, it's the low phase, median, high, and extra high, the 4 phases. Good. So firstly, to the overall result, because the energy, during this test, the energy was actually measured after a charging station. So in the original paper of the MMP EVM, they assumed there was a 10% charging loss. And here we just made 2 additional charging losses assumption to see what is the differences. And so then you can see many numbers here. And firstly, you can see that Habiba flow is insensible to vehicle characteristics. All the values remain the same. It doesn't matter which kind of vehicles you would like to address. And when we look at with a charge loss of 10%, we can see that actually our result corresponds to the result in the original paper of MMP EVM. And we also see that the MMP EVM actually best match, their estimates best match the data from the manufacturer. And PHEMlight 5 tends to overestimate the energy consumption, while the EVM tends to underestimate the overall energy consumption for the all vehicle types. And according to the consumption ranking, actually they are all the same except Habiba 4, and that means the heavier the vehicle, the higher the energy consumption. And we also tried to use the SUMO default setting for each model, and then the results show that actually different model uses represent different vehicle types in this case. So to the cumulated result, we can say here that I just order them according to the vehicle weight from light vehicle to heavy vehicles. So you can see that the cumulated energy consumption of PHEMlight 5 that is indicated in green is very close to that of Habiba 4 when the vehicle is relatively lighter. These are the first 2 pictures you can see. And when the vehicle is getting heavier, and then the difference between these 2 model estimates is getting larger as well, especially in the high speed phase here and here. And you can also see that the accumulation curves of EVM and MMP EVM are quite similar to each other. It doesn't matter if this vehicle is light or heavy. They have very close tendencies about energy consumption. But you still can see a little bit at the high speed phase, the MMP EVM tends to estimate higher energy consumption. So moreover, we look at also the relationship between speed acceleration and energy consumption. And here I just show you the example of the result of BMW i3 with EVM model. And then you can see here that EVM can address, so again, the x-axis is the acceleration interval, and the y-axis is the speed interval. And the average of the respective energy consumption is displayed in each cell. And then you can see that the red means positive values, and the blue means the negative values. And here you can say VEM can actually address the energy recovery situation. That's the blue part, and also the energy consumption, that is the red part. So that's only for one model. Now we see the results from the 4 models. Then we can see that actually all models can address energy recovery and energy consumption for propulsion. And here, if you have a very good eyes, you can see that the MMP EVM tends to estimate higher energy recovery than the other 3 models, and the PHEMlight 5 tends to estimate higher energy consumption at high speed and high acceleration. Here is the difference between the model estimates. So you can see here the higher difference occurs between the EVMs and the Habiba 4 estimates. That is here on the left side, on the left-hand side, and it shows that the Habiba 4 tends to estimate more energy consumption. That's the red part, and less energy consumption for in comparison to EVM. And the difference between the EVM and the PHEMlight 5 estimates, they are quite limited, so mostly less than 0.8. And at the end, the difference between the EVM and the MMP EVM's estimates is the smallest among all. That means these 2 models are almost similar, quite similar. So then here you can see another example with VW ID4 with EVM. And you can see that when the vehicle is getting heavier, the difference between the EVM and Habiba 4's estimates is also more significant. That means Habiba 4 will estimate more energy recovery at high deceleration and more energy consumption at high speed and high acceleration. And the other 2 plots there remained almost the same situation than before. And in addition, we also did the fitness check by scatter plots. And here we can see that the estimates of EVM and MMP EVMs agree quite well to each other. And regarding Habiba 4 and the PHEMlight 5, we see that the overestimation or underestimation is kind of more or less systematic. So we look at further with the results of the heavier vehicle from VW ID4, and it is the same, almost the same situation, the phenomenon we can see from here again. So it appears that there's a relationship can be perhaps determined to derive one model's estimates from those of the other model. It could be the case. So now we are finished with the first case study. Now we move on to the second case study. It is a highway scenario with constant travel speed. And indeed, such situation rarely happens in reality. It's quite more or less artificial, but we have the real data from the manufacturers. So we construct this in SUMO, and there were 100 battery electric vehicles in the simulation. And again, here we can see that the EVM, actually, the EVM's estimates best match the data from the manufacturers. In comparison to that, the PHEMlight 5 and the MMP EVM estimate more energy consumption than the real data. But both of them, they are very close to each other, the result. So it implies that actually both of the models tend to estimate higher energy consumption at high speed. The last case study we did is we used the published SUMO scenario Acosta. The main purpose here is to examine the effects of different loads and the constant consumptions at different temperatures, and to see if our parameterization works. So that's the main purpose that we did this case study. And there are around 9,000 vehicles in this simulation environment, and vehicle acceleration, deceleration could occur due to vehicle interactions, approaching intersections, or leaving intersection, and so on. And the 5 vehicle types were considered here again, just like what I mentioned before, and they were used and randomly selected to replace the original vehicle type of each vehicle in the simulations. Then we have a scenario only with these 5 vehicle types. And moreover, we also considered 2 load states. That's one is 0 kilograms, and the other is 350 kilograms. Yeah. And we also consider 3 different situations of constant consumption. One is for mild weather condition, cold weather condition, and warm weather conditions. And here you can see the result on the top. It is the energy consumption with and without loading in a mild weather condition. And you can see here that actually, except HAPIVA 4, not only EVM and MMP EVM, but also PHEMlight can reflect the effect of different loads. And in comparison to EVM, PHEMlight 5 and MMP EVMs, again, tend to estimate more energy consumption for a given additional load. And the 2 pictures on the bottom shows the potential effects of different loads, and also the constant consumptions at different temperatures, cold, mild, and warm. And we can see that PHEMlight 5 estimate higher energy consumption than MMP EVM, and then EVM in all state combinations. So to the next steps, as I just mentioned in the finish check, there seems a relationship, systematic relationship between the model estimates. So we think that more data is needed to confirm this. If it is the case, then a conversion mechanism between the models could be developed. So that means we can just convert the result from the HAPIVA 4 to another model, or the other way around, if that's the case. And we would also like to further analysis, to do the analysis with different car following models to see what effects they will have on model estimates. Maybe all these differences are not from the energy consumption model, but from the car following models, because they are different speed or acceleration, something like this. And we also want to do more comparison and sensitive analysis of each energy consumption component, because right now we only see the aggregated result, but actually behind this aggregated result, there are also results for example, for the air resistance result, for the rolling resistance result, something like this. So maybe we can do this for each component and to see what's the difference between the models. So thank you very much for your attention, and I'm happy to answer questions and have discussion with you.